All right, welcome everyone. Today we're going to continue our derivative rule discussion and look at some of our derivatives of our trig functions, okay? In particular, the sine and cosine, from those we can derive the remaining trig functions, tangent, cosecant, secant, cotangent, using our product quotient rules, in particular the quotient rules from derivatives that we learned previously. Okay, so let me start to share my doc cam and we'll get going into that work. All right. So for our derivatives of these trig functions, in particular, the sine and cosine, and maybe from our trigonometry, we might recognize through our identities, reciprocal and ratio identities, that tangent, cosecant, secant, cotangent can be already written as sines and cosines, right? Tangent, sine over cosine, that rational expression, that fraction. And from there, we can use our derivative rules for quotients to find those rules, okay? And so in order to deal with these though, here we will need two special limits to help create these differentiation rules, right? Because we're going to use the limits differentiation rule, writing and speaking at the same time, there we go, right? We're going to use that limit definition to create the derivative rule for sine, the derivative rule for cosine. And so since we're using a limit, we need these two limits, special limits that show up, okay? The first being, and you may remember this from a practice problem I provided in one of our homework sets, that if I take the limit as theta goes to 0, right, whatever the variable symbol I'm using, theta going to 0, and our derivative is going to be h is going to 0, okay? But if we have this ratio, the sine of that angle, theta, that variable, over that same exact expression, that same exact angle in the denominator, right? In our direct substitution, sine of 0 over 0, sine of 0 is 0, 0 over 0, that indeterminate form, right? And so some geometry you can kind of search on the internet, I'm sure. In the textbook, it might have it, a longer derivation of this. But for now, if we went back to our just simple calculation, letting theta in terms of radians, degrees, go to 0, taking the sine of 0 over 0, getting closer and closer, 0.1, 0.01, 0.01, so on, we'll see that this limit, that ratio, okay, is going to go to 1, okay? And a second limit that we'll need, the same limit as theta goes to 0, or h goes to 0, x goes to 0, of the cosine theta minus 1 over theta. In this case, again, as theta goes to 0, cosine of 0 is 1. 1 minus 1 is 0 numerator. Theta going to 0, 0 over 0, another indeterminate form. But in this case, this limit goes to 0. And we can do that through inspection, or again, searching in the textbook, search online, you might be able to find a little bit lengthier, more elegant kind of derivation creation for why these two limits and their results occur. You can look that up. But for now, we'll take it for granted to identify these results, okay? So then with that said, so now, in particular, when I want to take the derivative with respect to x of the sine of x, what is that going to be? Or likewise, taking the derivative of the cosine, what would that look like? Again, we'll do tangent, cosecant, secant, like I said, later. Okay? So with these two limits and this information, let's start to manage these differentiation rules. Okay, so first up, let's look at the derivative of sine of x. Okay? Right, so that's y is equal to the sine of x, that function, or f of x equals sine of x, however you want to write that. Or we do theta instead if that's your independent variable choice. F of theta equals sine theta. But there we go. Taking a derivative of the sine of x, or if you want to see his indices here, the sine of x, there's my function acting on x, okay? In terms of our limit definition, this is the limit as h goes to 0, sine of x plus h minus the sine of x all over h, right? F of x plus h is replacing my argument where we're evaluating the function at x plus h minus f of x, original sine of x, all over h, and taking the limit as h goes to 0. Okay, let me get that page out of the way. All right, so now looking at this, one tool we're going to use the sum of angles formula. All right, for these trig functions, where if I have the sine of alpha plus beta, right, my two angles is going to be the sine of alpha times the cosine of beta, plus keep the same symbol, the same operation, switching my angle sine beta, cosine alpha. Okay, so now in this case though, my alpha is x, beta is h. So then that limit as h goes to 0 becomes now sine of x cosine of h. Right, so there's my alpha and beta plus sine of h cosine of x, just switching my order there, which function, which sine, cosine gets the h and the x. Then I still have that minus sine of x all over h. So there's the big trick here, the algebra trig step here, using this identity, this formula, okay, to make that swap. Then now comes just our reorganization, our rewriting, kind of like when we were adding, subtracting the same value in our product rule, quotient rule discussion previously. We're going to take this limit as h goes to 0, steal everything over h. And all I'm going to do really in this case is bring the sine of x term together with this other sine of x term. Okay, so I'm going to keep this kind of color coordinated. This one stays the same, but now this minus sine of x, I'm going to bring over to the middle, if you will. That plus sine h cosine x, I'll bring that to the end. Okay, so there's a reorganization there. That's all I'm doing. Now, the whole bit about our fractions, right? The fact that if we have here a plus b over c, that's the same thing as having a over c plus b over c, okay? I'm going to separate my fraction, my rational expression, because now, for this pair, sine x cosine h minus sine of x all over h. Okay, then to that, I'm going to add this piece sine, or I guess I could put in green, plus sine of h cosine of x all over just h. And I'll put this in a big bracket. It's still together underneath that limit. I've just separated one rational expression, one fraction here, the other like so. Okay? So separating those components, keeping the same denominator. This is when those two special limits are going to become relevant for us. So taking this limit as h goes to 0, okay? And in this case, I'll be a little bit tedious and let me do this extra step here. The limit of a sum is the sum of my individualized limits. Just to get this all one color now for one step at least. Okay. And now, with that said, I'm gonna get a second sheet of paper here. All right. So just seeing where these manipulations came from. Now, here comes some of the algebra work to get those two special limits to show up. So in this first one, right, we can see they both share that same sine of x. I'm going to factor out that sine of x. And when I do that, what's left over? Cosine of h minus 1, right? Sine x I brought up front. Divide that, we need a placeholder so that 1 shows up. Plus this limit as h goes to 0. And in this one, what we're going to do kind of with this next step on this as well, I have the sine of h times the cosine of x all over h. So what I'm going to kind of do is separate that product, similar to kind of how we did that addition, but now with that multiplication, that cosine of x can stay, or you could put it over 1, right? Because if we're to multiply across the numerator denominator, we're right back where we started. So I'm kind of separating that product into their own individual fractions, if you will. I'm going to do the same thing over here in just a moment, okay? So here, let's do that. I have my sine of x times cosine of h minus 1 all over h, plus this limit as h goes to 0, sine of h over h times just the cosine. I think I mixed up my color coordination here compared to my special limit discussion earlier. I should have these two in red, but that's all right. Right, all that work we had done before in hopes of getting that differentiation rule for sine, right? We had done that work, we're down to this stage, all right? Now, as we go through, again, a little bit longer step here just for the sake of discussion, all right? When we look at this, this limit depends on h. Just saying, okay, as h goes to 0. So if I was imagining doing this by hand, by calculator, letting h go to 0, letting h be 0.1, 0.01, 0.001, so on. When I go to plug in those values, the only expression that's really changing are those pieces that have h, right? That sine of x is unaffected, right? It doesn't identify, it doesn't kind of keep track of what h is doing. It's just the sine of x. So this is like a constant in that respect. It does not change with respect to h. It doesn't care what h is doing. Similar for that cosine, right? So those are kind of like what we say, constants. So I'm going to be able to bring those components out. All right. So this is going to be the sine of x times the limit as h goes to 0 of that cosine of h minus 1 over h. If you want to keep that in brackets, we can. Plus, and now again, that cosine of x, it doesn't change as h changes. As we let h go to 0, that cosine of x is unaffected. But we do have the sine of h over h in that limit as h goes to 0. And these are our two special limits. And again, I know I should have more accurately color coordinated. Cosine h minus 1 over h, or instead of h, now we have thetas, or instead of thetas, we have h's. This limit, 0. This limit, sine theta over theta, as theta goes to 0, h over h, h going to 0, that's going to be equal to 1. Okay? And we take that for granted, or from previous work. We can take a long road to derive those, look in the textbook, look online, or our calculation route to see. So now, doing those limits though, we get the sine of x times 0 plus the cosine of x times 1 So going back to it, when we took that derivative of the sine of x, that limit definition, sine of x times 0, 0, right? And this is just cosine x. So the derivative of the sine of x, cosine of x, it just does a switch, okay? So whatever it might be, we can start to take those quick derivatives. So for example, right, if we're given y is equal to 4 sine of x, right, that coefficient in front of the sine, if we want to find y prime, that derivative, the derivative of 4 sine x, 4 comes outside, derivative of the sine of x becomes cosine x. And again, whether you want to use those parentheses around the x or not, you can choose, right? So y prime for cosine of x. Okay, a little close on my box there. Okay. Taking the derivative of that sine. And so once we've done that limit work once to get that rule, we don't have to go back to using limits, thank goodness. Now we take it for granted, just like our power rule for polynomials. Now we have this differentiation rule for the sine. Okay. And so I won't necessarily go through the full action for the cosine. You can definitely practice and go through those steps as well. But let's check it out. Okay. This start. So we have y is equal to the cosine of x, or f of x is the cosine of x, with or without those parentheses around the x. When I take that derivative of the cosine of x, moving into that limit definition, all right, going through this one time or we get our rule that we can apply over and over again. Just like we did before, we're going to apply that sum formula. Now for the cosine, we get the cosine of x, cosine of h. Okay. But in this case, it does the opposite sign. Since that's an addition, we subtract. We go sine x, sine h. Okay. And so through similar factoring, reorganizing, I should say first, then factoring, okay, is pretty similar to what we had just identified. What we're going to find, okay, so if you follow that pattern we did with the sine derivative a moment ago, what we're going to see is that when we take the derivative of the cosine function, watch out, we're going to get this negative lingering, okay? It's going to be equal to the negative sine of x, the opposite sign. You turn the positive negative, negative sine of x. So we get this negative showing up, okay? So, for example, if we have f of x was equal to 3 cosine of x, then what's that derivative going to look like? It's going to be 3 times the derivative of cosine of x, right? That constant comes out, taking a quick shortcut there. And the derivative of cosine, negative sine of x. So in the end, my df dx, or f prime, whatever you want to call it, negative 3 sine of x. Okay, and again, whether you want to use these parentheses or not, it's up to you. The big thing here is that that negative starts to show up. Okay, and then if we start to see combinations, just watch out for those signs, those operations involved, right? So for this next example, what if I want to differentiate say here, g of x was equal to 4x squared plus 9 sine of x minus 6 cosine. And later we'll bring in product quotient rules as well, okay? But if I want to differentiate here, g prime of x is equal to, and just going down the set of terms here, right? My coefficient 4 stays. The derivative of x squared to x, that power rule. And then now with our 2 trig functions, plus 9 sticks around, the derivative of the sine, cosine x, the minus 6 stays, derivative of the cosine, negative sine of x. All right, so taking the derivative, my coefficients stay up front. And lastly, just simplifying later on when we get more comfortable with these steps, we can just jump right to our solution. But for now, showing those steps, 8x plus 9 cosine x plus 6 sine x, right? Negative 6 with a negative sign, negative, negative makes positive. And there we go. Okay, and this is just our trig if you want to label label, right, and derivative sine and cosine to get those results. Okay. Next up, let's do this one. Let's find the derivative. And what if we have here capital F of x is going to be, let's say here, 5x cubed cosine of x, right? So if that's our function we're trying to find the derivative of, just to really reinforce here, we have 5x cubed times the cosine of x. That's what that function is telling us. So in that case, I'm just really trying to enforce that we're dealing with a product rule. So as we're going through these derivative rules, problems finding the derivative, what was helpful for me, and when I start to work on these problems, organizing, is write which rule we're using, okay? And for the product rule, remember, if we have f times g, it's f prime times g, the derivative of the first function, times the second, plus f times g prime, the original first, times derivative of the second function, right? So with my function over here, my first function, lowercase f, little f, 5x cubed, its derivative, power rule, right? 3 times 5, 15, x squared. G, my second function, the cosine of x, its derivative, which we just glanced over that derivation, that creation of it, negative sine of x. So there's my components I'm going to need. And again, another tip for organizing, write out what components we need. So that way, when I go into creating my derivative, then my capital F prime, my derivative of that function overall, that product, we're going to get f prime times g, I'll leave it in black ink, plus f, which was 5x cubed in black ink, times g prime, negative sine of x. Okay, so just kind of really trying to make those derivatives jump out. The original function, I'll leave in black ink, but it's still that combination of those components. So f prime, 15x squared cosine of x, minus 5x cubed sine of x. And at this stage, I'm not going to worry about trying to factor out a 5x squared and have some response. We can, but it's not going to be that much more helpful, supportive on our understanding, right? There's no trig identities we can use to kind of condense. Later on, there might be some, right? Cosine squared plus sine squared equals 1. There'll be those instances where we can possibly simplify or reduce, but not so much here, okay? The big point, the product rule being applied, and those derivatives are individual components being put in place with that formula. Okay, and so then with that said, let's set up now how we can use that quotient rule to get our other trig derivatives, or other trigonometric functions derivatives. Okay, so just remember, if we're taking the derivative of a quotient, f over g, not meant to be double, but make that visible, the derivative of that quotient, f prime times g, numerator derivative, times original denominator, minus f times g prime, numerator function original, times derivative denominator, all that over your denominator, original denominator, squared, right? There's our quotient rule. So then that rule alongside some of our trig identities, we're going to be able to create the differentiation rule without having to go through the limits, okay? And so in this case, this becomes the numerator for the tangent with that ratio identity, the sine of x, denominator, cosine of x, right? Tangent sine over cosine, doing that rewriting. And now, with our quotient rule, right, f is going to be the sine of x, its derivative, cosine x. G, the denominator function, cosine of x, its derivative, negative sine of x. So then, putting that quotient rule together, f prime times g, I'll leave this one in red here, minus f times g prime all over my denominator g squared. Okay, so there's that quotient rule applied to that ratio, that fraction, that quotient of sine over cosine, which was our representation of the tangent. And now, simplifying, cosine times cosine, the cosine of x squared, or the cosine squared of x, negative, negative, positive, sine times sine is sine squared x, all over the cosine of x squared, or the cosine squared of x. I'm not going to try to cancel. Okay. I can't cancel with that addition anyways. We have to break that fraction apart. But in the numerator, our Pythagorean, our common trig identity, makes its appearance, right? Cosine squared theta plus sine squared theta, or in this case, x is equal to 1. So the numerator is 1 all over the cosine squared of x. And here a little side note, 1 over cosine x is equal to the secant x, right? Or cosine theta. 1 over cosine theta equals secant of theta. And that squaring, just kind of like we saw here, we can transfer in. So what we found with all that said and done, that quotient rule applied, 1 over the cosine squared, secant squared x. Okay, one of the important ones that does kind of show up a lot in examples and problems of the future, that the derivative of secant is, or the tangent, pardon me, is secant squared. Watch that exponent. Okay, so we can use that quotient rule to create this differentiation rule for the tangent instead of having to go through the limits. Okay, and so then the others, I'll let you practice and create, right? That the derivative of the cosecant of x, the cosecant, 1 over the sine of x, the secant, one over the cosine of x. We just talked about that identity, that reciprocal identity. And then the cotangent, the reciprocal of our tangent, cosine of x in numerator, sine of x in denominator. So with each of these, you can go through the quotient rules to produce the differentiation rules for these last three trig functions. The numerator function, a constant 1 for these two. And then this one very similar to what we just saw for the tangent. And you can kind of look at those identities, see what results, okay? They have in the book, you can follow there as well. What I would say, and truly what I kind of go through with, when I see those cosecants and cotangents, I don't really have those memorized. I just go through these steps to do the quotient rule to find those, okay? But what I would kind of say at this point, I'll ask you to memorize the results rules for sine, cosine, and tangent. The others we can recreate, but the ones that I want to ask you to memorize, right, that the derivative of sine is equal to the cosine, the derivative of cosine is equal to negative sine, and the derivative of tangent, which we just finished, is equal to that secant squared. Okay, those are three that I definitely want you to know, because those get used over and over. And like we saw with our identities, any trig function can really be rewritten in terms of sine and cosine. And we can just use our product rule, quotient rules, whatever else we might need to do in manipulating those functions from there. Okay? All right. If you have any questions on those, let me know. Otherwise, there's our introduction, our work with the derivative of the trig functions, sine and cosine, definitely the foundations. Okay. Take care. Questions, let me know.